was upset about the snow as well.
Well, you make it come through the ice of the snow. That's what happens. It's all your fault.
All right, I wanted to prove a property about solutions, right? So we had EFT.
I have a question before we get started.
Yes.
The homeworks that were due, we only went through the Bernoulli equation, and 2.9 miscellaneous had some of those in it.
It had one at the end.
Can you extend that deadline like one more day so that we
And one of the
can
problems
finish
also
it?
had the integration factor, integrating factor.
Yeah, well, that I actually spoke about the integrating factor before the
Well, can we get one more day to finish it? Because we were down to the last three. Come on, back me up here.
Yeah, of course, right?
Well, she's right.
She's right.
Is that supposed to be Q of t twice?
This is supposed to be
R.
R. All right, so we had that equation, and I wanted to show you two things. That suppose y1 is a solution to 4, then so is C1 y1. C1 is just an arbitrary constant. There's also another fact. Suppose we have two solutions, y1 and y2 are solutions to 4. Then so is their linear combination, C1 y1 plus C2 y2. This is called a linear combination. Or again, C1 and C2 are just arbitrary constants. And it's not a difficult thing to prove. You just have to sort of plug and chug and do the computations, right? So for the first one, the first bullet point, right, if y1 is a solution, then it means that if you take p of t times y1 double prime plus q of t times y1 prime plus r of t times y1, you actually get g of p. No, we're looking at the homogeneous case. Just the other cases we have to do something. Okay. All right, so remember what it means to be a solution. It means when we plug this function into the differential equation, it makes sense. That's what it means to be a solution, right? So then, I'll just write p here, just to save time. If I replace this guy, what's the derivative of this, just so we know? Right, it's just a constant, so you just ignore it and then you take all the derivatives, right? So that means I can plug this in to here, y1 double prime. This gives us just p times c1 y1 double prime plus q times c1 y1 prime plus r times c1 y1. And what happens is, because this is a constant, you can sort of just factor it out. Prime plus r times y1 equals 0. Right? It's a constant. It's a constant factor. The derivative won't affect it. And we know from before that this was 0. So that means C1 y1 is a solution. Right? Because if I plug in a constant times this thing, the equation is still true. So that means it's a solution. Similar, if we do this, then if we take the derivative, we would get that. If we take the second derivative, we would get that. So we would be able to write this as C1 times and because this is equal to 0 because y1 is a solution, and this is equal to 0 because y2 is a solution, the equation is true. And so C1 y1 plus C2 y2 is a solution. So one property of linear differential equations in general, not just the second order, but here we're specifically talking about the second order, is if I know a solution, then a constant times that thing is also a solution. And if I know two solutions, then a linear combination of those two solutions is also a solution. What else do I want to say? Now here's something I'm just going to mention, which it's not really justified until 3.2, but I'm going to say it anyway. I'm also going to mention this phrase, linearly independent. Anyone knows what that means?
They don't have, they cannot have two similar terms occur at the same time.
They can't be written in terms of the other.
Linear?
Right, one cannot be written means one cannot be written as a constant times the other. Then any solution to 4 can be written in the form So let me explain what is happening here. Right? Provided y1 and y2 are linearly independent, that simply means you can't write one as a constant times the other. Why do we not want that? Well, I just showed you that if y1 is a solution, a constant times y1 is also a solution automatically. Meaning, if these two were, one was a constant times the other, it would be redundant. I'm really only giving you one solution, right? Because we already know that the constant times it will also be a solution. So what we want to do is we want to get two functions where I can't write one as a constant times the other, so we don't have any redundancy. And provided we can actually do that, any solution, any one, you can write in this form. So if you have a second order linear differential equation, the solution will have this form, is basically what I'm saying. So I want to write it down. One way you can see this makes sense is, since you have a second order linear differential equation, right, we have a y double prime. To end up solving for y, what do we have to do, essentially? We have to integrate twice to get to y, right? Each integration gives you a constant of integration, right? So you expect whatever your answer looks like to have two arbitrary constants of integration, right? The fact that it also has this form, you can sort of think of it from the separation of variables standpoint. Remember the first equation we saw, y prime equals y. When we solved that, we had that c times the e to the x, right? So it's c times that function, right? It's not really a justification, but it's sort of giving you an intuition as to why this is true, right? But in general, this is true. I wrote that down, but I don't feel like writing this down. So we're in the facts stage about the second order linear equation. Some facts. Another fact. Again, it will be justified more in 3.2. There's something called an initial value problem. It simply means I give you a differential equation and the initial condition.
So then you would be given two initial values.
Right, we'll need 2 plus t plus ty equals 0, where I would give you the y value at some point, and I would give you the y prime value at some point. We can further say every solution to a second order linear differential equation will have that form, and if you give me initial conditions, I can write the solution in this form. C1 and C2 are arbitrary constants, but I will definitely be able to determine their values that will make everything here work. Right? Those are some big claims we sort of justified in 3.2, but I thought I'd just tell you about it. Putting this all together, well, not yet. That's getting too excited. I'm jumping into that. Okay. Note, we need 2 initial conditions. You can't really solve one equation with 2 unknowns. That's why we actually need 2 equations so that we can get to those 2 unknowns. That's just another fact, sort of algebra fact. Right. These are some general facts. We will go over them in 3.2. But they're good to know, so just for the language I'll be using in the future, I should know this stuff. Finally, we get back to 3.1. So section 3.1 gets even more specific. It doesn't think of these guys as, it thinks of these guys as constant functions, right? So we had, in general, what a second order differential equation looks like. Then we found out what a second order linear differential equation looks like, is this one. Then the second order linear differential equation that's homogeneous means there's a zero over here. Then we specialize even further to the second order linear differential equation with constant variable. It seems like we're just dumbing everything down, but actually, these are worth studying because they have tons of applications. All over the place. Physics, mechanics, electric circuits. All over the place. Right? When you take physics 1 and you get those law equations of motion, where do they come from? A second order linear differential equation with constant coefficients, right? You assume the acceleration was equal to gravity, right? Basically, you're assuming that y double prime is a constant. You integrate twice, and that's how you get the equation y equals 1/2 at squared plus v naught t plus y naught, right? It came from solving a second order differential equation. Mechanics starts out with this, right? Now, you probably didn't know that's what you were doing, but that's what you were doing. You were solving a second order linear differential equation. These guys are very useful for, well, all sorts of motion, especially linear motion. Anything that moves in a straight line, or anything that moves in a straight line and oscillates, right? So if you're talking about any linear motion, free fall, you'd use a second order linear differential equation with constant coefficients. If you're thinking of the motion of a piston or a shock absorber, you'd use a second order linear differential equation. Right? Tons of things in electric circuits, you use a second order linear differential equation with constant coefficients all over the place, right? Spring systems, you model them with this equation, like tons of things, really. So when we're saying, oh man, we're now to this simple form where everything's constant, everything's too nice, and you know, why do we care? We care. Like, there are lots of things that you model with equations like these. Right? And there are other things that where you can't exactly model them like this, but this will provide a good approximation. Right? So that's something to consider. So dealing with these guys is actually very important because you will come across it, right? Especially mechanical engineers, electrical engineers, you're going to be dealing with these kinds of differential equations all the time, right? So knowing how to deal with them is a good thing. All right, so, and that's actually the focus of 3.1. 3.1 tells us how to solve these. Let's illustrate. Let me give you an example and we will solve it. So I just gave you some general rules about, you know, how these guys behave, what it means to be a solution, and how solutions behave with linear combinations and arbitrary constants. Let's actually do one. Let's say I gave you that differential equation. Yeah, that's good. So, how would you solve that? You make a guess, right? We guess that y looks like e to the rt, right? So you assume y has this form, which is your solution. This would mean that if I take its first derivative, I get e or t y double prime, which gives us r squared e to the rt. Which means, since this is a solution, what it means is when I plug all these guys into this equation, it makes sense, right? So I'm going to plug them in. Now, if we want to solve this equation, what would we do?
We simplify by the RT.
Right, e to the rt is a common term. We can factor it out. Since this guy is never zero, because it's an exponential, that gives us the fact that this is 0. Right? And how do we solve that? We can factor. What are the factors?
R minus 3, R minus 1.
Right, r minus 1, r minus 3. Which means our solution for r is
3 and 1.
right? So there, you can sort of count them as multiplicity. There are two solutions to this equation, 1 and 3. This means the solution is y equals
C1.
right. Let me write it. I want to write this one out in detail. I'll tell you how to write it shorter later on. This means we have two solutions, right? I just want to emphasize what we've been writing about before, right? Either y is equal to e to the 1t, or y is equal to e to the 3t, right? Because I just solved for my r, and I assumed it was e to the rt, so it's either e to the 1t or e to the 3t. But what do we know if we have two solutions to a differential equation? Well, it means the linear combination is the solution. This is called the general solution. That's sort of how you solve this, but if you have a second order linear differential equation with constant coefficients, you always assume y equals e to the rt. Things pretty much play out as they do there. So what you can sort of do is ignore all those intermediate steps and just jump to that quadratic equation there. Once you find r, then you jump to here. I'm going to write out one so that you see, if you're writing it on a piece of paper for an exam, how you do it. You wouldn't write all this. It's not necessary.
If y is always missing, I could just do the drop-it factor. I need to do that, right? Or this could be done if y is missing.
If the y was missing, this can still be done. Yeah. Anything of this form, if one of these constants are 0, it still works, right? As long as a is not 0, because if a is 0, it's not a second order differential equation anymore. But yeah, these a, b, c are arbitrary, so you can always do this once you have constant coefficients. And this is called the general solution. Still requires some justification, but that's what 3.2 is about. But that's how it would look. So,
yep. So in the last chapter, when we had that v substitution, we would say, a y double prime plus b y prime equals some constant. So can you just do this instead of substituting?
that's not as general as you would think. When we did that substitution, remember, it was the y was actually missing. So we can say v equals y prime and v prime equals y double prime, which gives us a first order differential equation.
Okay, so why would we ever do that once we have this now?
Because we have a y here. Right? If your v is equal to y prime, what would y be equal to? The integral of v. Y would be written in an integral. So you'd have an equation with a derivative and an integral in it. It's no longer a differential equation. None of our techniques would work.
The opposite. If we have one of the old ones, can we just do this substitute and just say that c?
Oh, if the y was missing,
Yeah.
it is a valid approach, yes. Right. But this one is far more general. And it will give you the same answers ultimately.
What is an equation with the differential, with the derivative and an integral in it?
We usually don't write them like that. It's just too much. It's just too much work. You do that if you have to, and then it's sort of like you give the integral a name. Like, here's this integral. Let's just call it I and move on, and we try to work with it. But it's not. Yeah, it's not very efficient to do that. Too many things are up in the air. Okay, so that's how you do it. So. I remember when I was learning this, there are two kinds of engineering students that I find. Right? There's some that only care about, okay, this is how the problem's done. You show them, okay, you pretend y is equal to e to the rt, you do all this, you get the answer. Okay, that's good enough for me. That's great. Right? And then there's a second kind that's like, why? Why does it work? Like, I just pretend y was some function. I did all this and got an answer. Would it have worked if I pretended y was a different function?
Yes.
Why did I choose y equals e to the rt? Why e to the rt?
They do cancel out.
Oh,
Because the derivative is always the same.
The derivative is similar. The
almost.
derivative is always a similar
Try to
term.
give a
That is why,
Quadratic equation.
right? So it's not just about that. It's about what he said. Remember when I gave you that first differential equation day one, y prime equals y, and I asked you to, guess a solution. And you guess e to the x, because you know that it's similar to its derivative. You have a derivative equal this function, and you know, oh, e to the x behaves like that, right? That's sort of what you're doing here. You want one side of the equation to equal 0, which means on the left side you need to be able to combine terms, which means they need to be similar terms, right? That's what we learned in algebra. We can only add similar terms. So I needed to pick a function where its derivative and its second derivative is pretty similar to the original function, right? E to the rt is the only function that we know of that has this property, right? So I couldn't just guess, y equals ln r, or y equals sine of t over r. Like, none of those really have what we're looking for, right? So these sort of differential equations, you always assume y equals e to the rt because that keeps it similar to its derivatives, which allows you to combine terms and get 0, which allows this to make sense. And this is the general solution. And I stand by it that any solution to this differential equation can be written in this form, which means if you pick some other function, it just would not work. That requires some justification. That was 3.2 is about, but everything can be this. Meaning if you don't pick the exponential, it won't work. Yes?
so we just need to pick one that with the respect t as the power, right? So can we assume y equal to x to the t or whatever to the rt, something like that?
No, because we wouldn't get similar terms. Right?
But we still can.
If y is equal to x to the t,
No, x rt.
x to the rt,
We can get x. No, we can get r. Y prime equal to r x to the. Wait.
Times ln.
Oh no, no.
well, it
No,
won't
that's
work,
just
right?
minus
So
one.
y prime would be r
No,
x to
no.
the rt,
Times ln.
and y minus 1. And y double prime would be what?
I see.
Now what's the problem with that when you plug them in?
Yeah, but x are
You can't really factor a common thing out. You're going to end up in trouble. Right? Then you have to worry about what if x is 0, what if it's not 0. There are cases where you plug this in, but this wouldn't be one of them. And we'll actually get to this in, I forget, maybe 3.4. You deal with guys where you actually pretend the solution is like that. But that's how we do it here. Let's do another example. Find the general solution. So, what's the answer? C1 e to the what?
Negative 2t plus c2 e to the t over 2.
So on a quiz or a test, this is what I expect you to write out. I don't expect you to explain all that. I expect you to know it. So you see this, you immediately jump to the quadratic. Right? Then you want to solve this. How did we solve that?
It's going to be negative 3 plus or minus the square root of 9 plus 16 over 4.
We could do the quadratic formula, but I'd probably prefer to factor first,
Oh, I just
if
shoved-
that can work.
I just shoved the
Right? So this here gives us 4, this here gives us 1, and I want to get to a plus 3, so if I take a plus 4 and a minus 1, I get plus 3. That's how we factor. So this means that r is either a half, or r is minus 2, which gives us the solution. Y is equal to c1 e to the t over 2 plus c2 e to the minus 2t, which is what was said before. That is correct, the general solution. I always try to factor first. If it can work, it's quicker than the quadratic formula. I mean, if you really love the quadratic formula, I guess you could. Like, I'm so about the quadratic formula. I am all about the quadratic formula.
Hey,
If that's you, then fine.
If you don't use it, you lose it.
Oh, you'll have opportunity to use it. Don't worry. We will use it all the time. So don't worry about that. There's a reason I asked you what it was on quiz 1. There's a reason why I asked you everything I asked you on quiz 1, actually. Everything I asked you, you're going to use it. So don't think, oh, I'm just messing with you. Yeah, you just testing us on stuff from algebra just to make us feel bad. No, everything I ask you, you're going to use. Kramer's rule, how to factor quadratics, cubics. You need to know that. Partial fractions, you need to know that. You've seen that already, but later down the road in chapter 10, you're going to be using partial fractions a lot. Where's that, chapter 6? When you do Laplace transforms. Yeah, actually on the first quiz, because it's stuff you need to know. Okay, so here, we actually already solved this one. The answer was y is c1 e to the t plus c2 e to the 3t, right? But now I gave you initial conditions. And what does that mean? I want to know what c1 and c2 are. How do I get to them?
You gave that,
Yeah, tell me the process. What do I do now if I have these initials?
y prime equals
Put
something.
the addition.
Well, first let's find the y prime because they told me something about y prime, so I should find that, which is
C1 e to t plus
3C2.
3c2 e to t.
so. What does this mean? If I'm given initial conditions, what does this mean?
It means C1 plus 3C2 is equal to negative
Plug
7.
in y0.
Right. Remember, the 0 what goes in here is your t value, and this is the corresponding y value.
C1 plus C2 is equal to
Meaning, if I plug in 0 into the original for t, the result will be minus 1, right? So I get c1 plus c2 equals minus 1. If I plug in t equals 0 into the second equation, I would get c1 plus 3c2 equals minus 7. So now I have a system of equations. I have two equations, two unknowns. How do we solve it?
Subtract it?
You can subtract. Your elimination method. Subtract the second one from the first one. C1 minus C1 dies. C2 minus 3C2 is minus 2C2. And this would give you 1 minus 7 minus a minus 7 gives you
minus
6. Positive 6. So this means C2 is minus 3.
Plug it back
This
in.
means you plug it back into either the equation would work. Let's plug into the first one, it's easier. So C1 minus 3 equals minus 1, which means C1 is equal to
2.
positive 2. And so this gives us the answer. C1 was 2e to the t minus 3e to the 3t. This is known as the particular solution. more terminology. The resulting if we have ay double prime plus by prime plus cy equals 0, assuming y equals e to the rt, gives ultimately ar squared plus br plus c equals 0. This guy here is called the characteristic equation. So you know the terminology. So if I say find the characteristic equation, that's what I'm talking about. And when you have arbitrary constants in your solution, it's called a general solution. And when you have no arbitrary constants, meaning you find what their values are, you call that a particular solution. And we will be talking a lot more about that also. Let's see. It turns out this is the optimal solution, as I said. Another thing to note, this is the only solution to meaning you couldn't find another solution if you tried. It would be a futile attempt, right? And that's sort of something great about these types of equations, which again, we'll get into it in 3.2. I can't help saying it now. There's something called the Existence and Uniqueness Theorem, which is one of the greatest things ever, right? It says for...
The sarcasm is real with this one.
No, it's true. It says if you have a second order linear differential equation, then as long as the coefficients are continuous, there is a solution. That's what the existence part is about. Meaning you're guaranteed to be able to find a solution. And secondly, it's unique. That's why it's called the Existence and Uniqueness Theorem. Meaning once you find a solution, that's the only possible one there is. Right? So one of the things that makes life hard, well, it makes it fun as well, but one of the things that makes life hard is sometimes the uncertainty. You don't know, right? You don't know
That's not fun.
if the answer you're seeking is out there, and you don't know if you find it, maybe there's a better answer. Maybe there was a better way to do what I just did. Here, there is no uncertainty in that regard. I found the solution, and I know that's the one, right? I don't have to look for anything else. I don't have to come up with a better way to get to it. This was pretty easy, and it gets me here. It's good enough. Right? I don't have to look for another solution. There is no other way to write a solution to that differential equation. Right? Anything else I write will be equivalent to this. And so you might ask, what about something like y double prime plus y equals 0? And you might say, note, sine is a solution to this. Right? If I take the second derivative of sine of t, I get minus sine of t. Right? Also, cosine t is a solution to this. If I take the second derivative of cosine t, I get minus cosine t. So if I add the second derivative to the original function, I actually get 0. Which means y equals c1 sine t plus c2 cosine t is a solution.
Why these two terms add together equal to 0?
Well, take the derivatives and plug it in. Right? Derivative of sine of t is cosine of t. Derivative of cosine of t is minus sine of t. So it would be minus sine plus sine. You get 0.
Oh, that's
The equation would be true. Similar thing would happen with cosine. And so you can say, ha, Javon, ha! I found a solution that wasn't exponential. Well, you actually didn't. And when we get to 3.3, you'll see why. Turns out that we can write sine and cosine as exponentials, and we'll figure out using this method how to get to those, but that's just a preview. I'm sorry I get too excited, I just want to tell you what's coming up.
With math.
What about y double prime minus 2 y prime plus y equals 0? Well, that would give you this guy, which when you factor that, it's a perfect square. And then you're like, I only have one r, but I need two solutions. Turns out, first one is the obvious, well, I have one r, so it has to be e to the t. The second one, as it turns out, is t e to the t. And then you might say, why multiply by t? Well, intuitively, in the same way that this guy is similar to its derivatives, so is t to the t, right? You take the derivative of this, you get something that's, this is a first degree polynomial times e to the t. Its derivative is also a first degree polynomial times e to the t. But later on, we'll see a method that will tell you why you always multiply by t. It turns out this is something you always do. If you don't have enough solutions, and some of them repeat, you can just multiply by t's to get the other solution. It turns out that you can't write this as a constant multiple of that, so it's linearly independent. And so our solutions. And so y equals c1 e to the t plus c2 t e to the t is a solution. We'll get to that in 3.4. Right? Just so. So I know there might be questions right around here. What if this happens? What if that happens? Well, by the way, this sort of thing happens when you do the quadratic formula and you get a negative under the square root, right? This is why I asked you about complex numbers. Again, if I ask you about it, you're going to need it. Right? The characteristic equation here would be r squared plus 1. The solution to that equation is plus or minus I, right? R squared plus 1 equals 0, r would be plus or minus I. That's where your sine and cosine comes from. Just to see where we're going. But basically, this is the method. You see a second order linear differential equation with constant coefficients. It's homogeneous. Even when it's not homogeneous, we'll talk about that later. You do this setup. Pretend your y looks like e to the rt, and then just follow your nose and find the r's. And sometimes strange things can happen, like you have no real solution. What will end up happening in that case, you'll get trig functions in there. And if you have not enough solutions, you end up multiplying the ones you got before by t. And we'll talk about why we do all this, but trust me, this covers every situation, what we just did here. Whether you have two distinct solutions or only one solution or complex solutions, we will be able to find the answer. And the answer will be unique, meaning there's no other kind of answer. That brings us to 3.2. And 3.2 sort of investigates why this is. And it introduces a guy called the Wronskian. I like to start off with a bang. This is theorem 3.2. I don't think it's the first theorem in this section, 3.2.1. It is the first theorem.
Yeah.
This is called the Existence and Uniqueness Theorem. I think I just mentioned it.
Just for my notes, the greatest thing ever, right?
In differential equations, it's one of the greatest.
Okay.
The greatest thing ever is probably Euler's equation.
That's pretty cool.
That's just like mind-boggling. And we're going to do it in this class. Yeah, that's where these guys are coming from. Euler's equation. Yeah. It's such an awesome course, isn't it? Okay. this is what the theorem says. The IVP, remember I said this means initial value problem, y double prime plus p of t y prime plus q of t y plus g of t, and I'm given initial conditions. As this is the existence and uniqueness theorem, why studying linear equations is such a rewarding experience. This guy, as long as their coefficients are continuous, all these functions are continuous functions, it is guaranteed to have a solution. In fact, exactly one solution. You find a solution, that's it. You don't have to look anywhere else. Right? That's the solution. Right?
Can you prove it?
No, this is way beyond our scope, actually.
I don't believe it.
If you don't believe it, that's fine. You can go read it on your own, but you'd actually need to know a lot of linear algebra and stuff like that to really understand the proof, so it's not really worth me doing it. And I'm not talking about the engineer's linear algebra, I'm talking about the math major linear algebra. It's actually pretty different. So yeah, it's outside of our scope. This is just one of the things you have to take on faith. Right, that you'll always be able to find a solution to this, and there will always be exactly one, meaning the solution is guaranteed to exist. 2, it is unique. Furthermore, I think there part that this is also mentioned in the theorem, I just forgot to write it. But the solution exists on the entire interval. So we not only have the solution, but I can tell you exactly where it will show up. You take the largest interval that contains t0, where these guys are continuous, and the solution will exist on that entire interval. Right? Beyond that interval, we're not sure if it exists, and it might not be unique, but if we're in that interval, we know that this is true. And like I said, the proof for that is pretty involved. Your I could also be of infinite length. In fact, the solution to this guy, right? Your constants are continuous on the entire real line. It means this solution that we got for this works on the entire real line, right? That won't always be true, but it is true. In fact, there are some problems that actually talk about that. So I'll give you an example. I guess we'll have to end after this example. After this, I talk about the Wronskian, but then to talk about that, I'd have to talk about Cramer's rule. We won't have time. So let's just do this and be done with it. Determine the largest interval where the initial value problem is guaranteed to have a unique solution? You don't have to find the solution, just tell me where I'd be able to find it. So this is the function t times t minus 4 y double prime plus 3t y prime plus 4y equals 2. I'm given that y of 3 is equal to 0. Y prime at 3 is equal to minus 1. Tell me where I would be able to find a solution that's unique and guaranteed to do so. Any ideas? If only we had a theorem that told us where we can find a unique solution that's guaranteed to exist.
This guy.
I don't even know if the answer is out there. It's a second order linear differential equation, which means this guy applies, but look at the theorem. What form should we have it in?
We should have in the form of y.
We should have it in standard form, which means that is the first thing I'm going to do. Divide through by t times t minus 4. Plus 3t over t times t minus 4 y prime.
We cancel the t's, right?
I can cancel the t's here. Did I say 2? Well, it actually doesn't matter. 2 or 0. Alright, because we can have g of t over that side. So here, yeah, I could cancel the t's, but this t is
Why
fine there.
aren't you dividing the two?
Because this is in standard form now. Which means that this guy here is my p, that guy here is my q, this guy here is my g.
Is that one?
Oh. Right? So now what does the theorem say? When can we have a unique solution?
When p, q, and g are continuous.
Right. We need these to be continuous. Right? We need these to be continuous. Calc 1, where are they continuous?
So it's continuous from negative infinity to and then union of 0 to to 4, and then union 4 to infinity.
Right, right, because your t cannot be 0 and t cannot be 4. I should mention, it's sort of dangerous to cancel the t's because even if this wasn't here, it still wouldn't be continuous at t equals 0. You have to realize that. Right? Sometimes you simplify and things will get messed up. So you have to be aware that yes, t cannot be 0, meaning this is where it's continuous, right? So what's the largest interval where I am guaranteed a unique solution that fits these initial conditions?
Well, negative infinity to 0 is mathematically the same length as 4 to infinity, right?
No.
Or are they not?
It has the same amount of real numbers in it, like lengthwise.
You meant like largest as in larger numbers? Or
the length of the
the
interval.
longest.
Yes. Largest means longest.
Negative infinity is.
I mean, like, I thought like larger number of it.
Don't forget we have initial conditions to worry about.
Oh.
Where should our function work?
That's 4.
It has to work when t is 3, right?
So
what do you mean?
So I can only pick the interval that has a 3 in it.
So 0 to 4 or 4?
Since 3 is in this interval, 0 to 4, and it's not in any of the others, this is the largest interval. This is the largest interval. This is the largest interval where we are guaranteed
The solution.
a unique solution.
The
right?
solution. The solution. Yeah.
Right? We're not saying that there are no solutions over here. There could be. There could actually be many. Right? But we're talking about where do we know that there's only one? Here. Right? That is the largest interval where we know there's only one, because that's the only interval where our initial conditions would work. And these are the only options because of this theorem. Right? So I know this thing has a unique solution. I don't know what it is, but I know it exists, and it is somewhere between 0 and 4. We will stop there. Next time we'll talk about the Wronskian and Kramer's rule, so you can look that up if you forgot about it.
Are they Russian?